I'd like to show you now the memory window. I'll just make a simple program here. It just has the value of 0 and then increments it by 1 in this case, and then we'll increment by another 2 here. Just a simple program so we can watch the variable I. If I build that, just to make sure it's working okay, it says down the bottom build started, build succeeded, so that's fine. What I'm going to do is to run it down to here using a breakpoint. So I will click the run button and it will stop at that position. Now I has got no value at the moment. If I were to press F11, then that will single step down to the next line, and I has got the value of 0, as you can see at the moment. What I'd like to do is to look at this in memory, and you'll see I've got the memory window here, memory 1, and I've also got a watch window which I'll explain as well. But in order to get these two windows, you need to go through, for example, debug windows, and then the watch window is here, and then the memory window is there. Now you may not all have that on all versions of C++, and they might be in different places as well, but you'll have to find that out. But that's the general principle of looking for the memory window and also the watch window. Well, what are they used for? The watch window is used for looking, well, what I want to do is to find the address of I. Now, the way I do that is I use the ampersand I. That means the address of I, and so I'm going to press enter, and then I can right click on this and copy it, and I'll copy it into here, in other words, to find out the memory address, but it usually comes with a bit of baggage here, so I'll just get rid of that. So you'll notice this thing is hexadecimal. That means these are hexadecimal numbers here. They go from 0, F represents 15, for example, and so on. I'll explain hexadecimal later. But at the moment, the little 0x in front of that's a giveaway as well. That tells you that the number is indeed a hexadecimal number. So if I press enter, you can see, very interestingly, you can see I. Now there it is there. That's got the value of 0. It's 4 bytes long. It's a bit strange the way it's organized, but an integer is 4 bytes long in this case. It can be different depending on the operating system, the length of an integer. But in this case, but it works from low byte to high byte. In other words, that's the smallest bit of it there. I'll explain that in more detail, but just for the moment, that there is the 0. If I therefore press the F11 key and continue down, I'm now about to increment I here, you see. So if I do that, bingo, look at that now. Okay, so that's got the value of 1. So you notice how they're in, what do they call it? When it's in the least significant byte is to left hand side. What's it called? I think big little ender. I think that's called. And they've got big ender as well. I think that's from some Lilliputian novel or something rather. Anyway, the little bit of it is at that very end of the number. So now what happens next, you can see here, you're going to increment it by 2. So if we do another F11, then look at that, it's incremented. It's actually incremented the whole lot, but the only bit that shows in red is the bit that's been changed since last time, which indeed is that bit of it there. So that can be extremely useful, and we'll talk about that when we're talking about structures and the way that stuff is in classes, the way that the data is organized inside memory. It's very useful, more from an instructional point of view actually than to see what's going on. It's not essential to understand binary numbers and hexadecimal as part of the course in C++, but I will try and explain to you binary numbers and then hex numbers as well. I'll give you a rather trivial example. Well, binary numbers, binary digits, 1s and 0s, actually digit fingers. So let me try and explain it in terms of this very simple way. if someone is trying to signal to you that they want to signal a certain number, they might want to order some ice creams across the room. So they put up their hand and they say, how many? Well, you could say 5 ice creams. No, but let's agree upon a code. If we agree that the thumb is going to represent 1, the first finger is 2, and you multiply as you go across, multiply by 2. If you had 6 fingers, it would be 32 with the next number. So then we agree and we say, well, if you put the thumb, if he or she puts the thumb and the first finger up, that will represent 3. 1 plus 2 is 3. If you put all fingers up, then that would represent 31 when you add all those together. Those 8 plus 4 plus 2 plus 1. How do you know that very, very quickly actually by the next number is going to be 32, so you subtract 1, it's 31. If you had no fingers up, that would represent nothing. So you've got 32 numbers altogether actually if you include the 0. If they want to represent indicate 5, then a 5 would be represented by that first finger up and the middle finger up. 1 plus 4 is 5, and there's no index finger here, so that represents 0 there. What you could do then is to agree that a finger up is represented by a 1, and so the 7 that we've just, the 5 I should say, here could be represented by no finger up. That's the what they call that pinky finger, I think, isn't it? The little finger is down, both of those down. The middle finger is up, the index finger is down, and the thumb is up. You see, so working in from right to left, that number is going to represent 7. So if someone said to you, well, from scratch, what does that number represent, that binary number, what does that represent in decimal? Then you'd say, you'd write these numbers, as many as you want, going across, multiplying by 2, and underneath them you would place the numbers 1 and 1. And so you would say the number 7. What am I talking about? I think I'm looking for 5. So 5 is represented as 1, 0, 1. And that would say that's a 4, and that's no 2s, and that's 1. They all add up to 5. So that is the binary representation of 5. Now, what about this one here? So I'll just put that in there, 5. Now, what is this number here? What does this number here represent? Well, once again, you put all your numbers, you stretch them out, multiplying by 2 from right to left as far as you like, and then you put in the binary representation. And so if I do that, that's a 1 there, and a 1, and a 0, and a 1. That's correct. Now, what does that number represent in decimal? Answer, you take 1, 8, 1, 4, so we've got 12 so far, and no 2s, and finally another 1. So altogether, that gives you 13. Finally, this one here, 1 and 3 noughts, is going to be 3 noughts. Yeah. And what does that represent? An 8 and nothing else, so that's just an 8. Now, if we want to do them backwards, 8, if I want to do them backwards, I'll put, let's start off with all zeros here. Now, to do it backwards, you take the number 7, for example. What is that represented in binary? Well, if we put the numbers and we take make sure the number is that the biggest number is 8, which is going to be bigger than the number that we're looking for. So you say, does 7 go into 8? No, it doesn't. So we make sure we put a 0 here. Then you say, well, does 4 go into 0? Yes, it does. So we put a 1 there. Now, what you want to do then is 7 subtract the 4. That gives you 3. And then you say, oh, you've got 3. Does 2 go into 3? Yes, it does. So you put a 1 there. Then you say 3 subtract 2 gives you 1. Does 1 go into 1? Of course it does. So that gives you the binary representation of 7. So just looking at this one again, 1, 0, 1, 1 represents 5. So if I just put that in there, 1, 0, 1 that is the binary representation of the decimal number 5. Now, how do you actually represent that in a computer? And the answer is, this is your microprocessor, or could be memory actually. And what you do, you put a voltage across the first leg. It's very hard to see actually, but the very first leg there, you put a voltage. The voltage is actually 5 volts. I don't want to confuse you by telling you that. But just think of it like a battery. You put a battery across there. I mean, computers, the voltages flying around a computer are not very complicated. They're all either on or off. It's not like you've got an analog signal and complicated waveforms. It's very simple. It's either that leg has got voltage or it hasn't. And the next leg is, if you can't quite see it, but the second leg here, let me assure you, should have a voltage of 0. And then the third leg along has got a voltage of a voltage of 5 volts. But that's got nothing to do with the 5 that we're trying to represent. So we've got voltage, no voltage, voltage. That will represent the number 5. So that's how a computer represents numbers. What about hexadecimal numbers? You'll see hexadecimals numbers quite a lot in computing. We came across it here, if you recall, that 4D represented 77 decimal. Let me show you how that is going to how that works. Well, we have the numbers, the ordinary numbers, 1 up to 9, but numbers between, if we have 10 is represented by A, and 15 is represented by F. Well, to put it simply, if you want to work out what 4D is, you always multiply the second number to the left, which is the 4. You always multiply that by 16 and add on the rest. So in that case, D. Now what is D? If you look down here, D is 13. So you've got 4 lots of 16, and then you've got 13 to add on as well. So that gives you a total of 77. For example, 5A, that means 5 16s 80, and then you add on the 10, gives you 90, and so on. That's the way that it works basically. You can try this out for yourself if you want to just try this bit of code and see how we print out hex. Oh, there it is there actually. So we can just run that and see what happens. That just gives us the answer here, that it's 12. Now this is the way of denoting hexadecimal, that it's denoted by the 0x in front of it in C++. And then we output the hex number, the equivalent. That's the equivalent. It'll do it automatically in decimal if you do that, because it's an integer. Now if you want to actually print it out in hex, you use this hex and then you print out the number, and you see it's printed out in hex for you. We could just confirm what we were just saying a moment ago about 4D if I were to stop the program and then try 4D in here. You can use this to find out what the equivalent value is. So I can just click on that, and that will give me the answer of 77, which is the 4D. Now so for example, if we just take another simple example, 2A, what does that represent? Well, the first thing you do, if someone says to you, what does 2A represent? Well, what you do, you put the numbers here, 1 going across, and you multiply by 16. If it's the third one, you multiply by 16 squared, which is 256, and then across. So let's just confine ourselves to two well, they're just 2 nibbles, they're actually called, but this represents a byte, by the way. 2A is a byte. Each byte's got 8 bits. So in this case, you see, you've got 2 times the 16 plus 10, and that gives you 32 plus 10 is 42. We could confirm that if you like. We'll output that here. We'll put 2A. It doesn't matter if you use small letters or big, then you can then just run that. and that should give us 42, as you can see. Okay, now you might say, well, why would we want to use hexadecimal? Well, how did it arise? Well, it's actually a shorthand way of writing binary numbers. Would you believe in the old days we used to write computer language just like that? You used to put a switch, and you'd switch that on, you'd switch that on, and switch this. You would, if you look at the old Cape Canaveral, you'll see a console full of those flick switches. Well, each of those represents, if you flick the switch on, represents a 1. So that's how computers used to be programmed, by directly putting the binary numbers in. Would you believe? Then I guess the next stage would be that hexadecimal would be a shorthand way of actually feeding that stuff into the computer. So that if you've got the number 2, the hex 2a, well, actually, let me just set all these back to 0, and that one, we don't really want that as being red, thank you. Now, if I said, let's look at 2a, and we'll do them separately, you see. The hexadecimal number 2a represents 42. Well, what about if we take them separately? So we've got 1, 2, 4, 8, and 1, 2, 4, 8, and the separate nibbles actually of the byte. Well, if we want to represent 2, you see that is like a 1 here, and a 0 there. If we represent the letter 8, sorry about this, that should be a 0 to start off with. If we want to represent the letter A, then A is 10. So we'd say, okay, you put a 1 here and another 1 here. So that represents 10. Let's now start again. We put all the numbers in binary from right to left, going up to, continuing on up to 128. Then you say, okay, take the number 42. Let's what does that in binary using this notation? Well, the biggest number that goes into 42 is 32, so you can put a 1 there. 42 subtract 32 is 10. Does 16 go into 10? No, so we leave the 0 there. Does 8 go into 10? Yes, it does, and leaves 2 over. Does 4 go into 10? No. Does 2 go into 2? You bet it does, so we put a 1 there, and that's all we've got left over. Now what you might notice now, if you look at these two numbers that were produced, they're the same. So you can see how we therefore, this is a shorthand way of representing all of that in a computer. It just makes it slightly simpler. You might like to think all these numbers here are 16 times bigger than all these numbers over here, and these numbers are always 16 times bigger than that, if you like to think about that. But at the end of the day, hexadecimal is really a shorthand way of writing binary. So when you see that 4D, you, as an exercise, you could string those out into binary digits, and that's how they actually talk to the computer at the end of the day, binary by means of those 1s and 0s which apply to the microprocessor.